Woo! I'm so excited. Today, we're going to be building the circuit that we have so far. If you haven't figured this out by now, I'm much happier building circuits and seeing how they work rather than doing the mathematics behind it. I guess when you're designing and building circuits, you kind of have to do the math because it's necessary. Otherwise, you never know what you're going to get into. So the math is important. I just dislike it. I like jumping right into to building. So that's what we're going to do today is we're going to build it. On the last video, we designed the circuit we're about to build. If you haven't seen it, go take a look. The other thing, if you haven't quite figured this out yet, each video that I've done so far builds upon the previous video. So yeah, I know there's a few videos in the behind that you're going to want to catch up on if you haven't seen it. Here's a link to the playlist, so it might make it easier for you. There's a bit to catch up on if this is your first video, but hey, if you're interested in this stuff, then you're probably going to want to see it. So recommend you do so. But today, we're going to jump right into the circuit. So let me get it up on the screen, and I want to show you where we left off last time. So I'll pull it up right there. Okay. Yeah, okay, we're good. So this is the circuit we had last time. And if you remember the things we talked about, what we wanted to do was just like that water slide example, we wanted to give our circuit a number of different paths that it can go down. And so we had, in this design, we had 3 different paths to go down. And we had these switches that will enable us to turn the path on and off. And if you remember, different combinations of the switches will give us different total currents. So for 3 switches, we had 8 combinations, which is really efficient. And it gives us 8 different intensity levels that we can work with. Okay, now if you also remember, one of the problems I pointed out with the circuit is that these switches, well, put it this way, these current paths can be pretty heavy. I mean, at the peak here, we probably have about 100 milliamps going through this current path. That's quite a lot for a regular switch. So we may not want to expose our switches to that kind of current. Here's an example that maybe it'll make sense if I say it this way. If you ever tried to stop a garden hose when it's running with your hands, you know how hard that is, right? I mean, you'll get messy wet trying to stop a garden hose with your hands. It almost can't be done. But the way you do stop a garden hose is you put a valve in place, right? And that valve allows you to put just a little bit of effort, and then you can turn the valve off. And when you turn the valve off, well, that cuts off the water, right? That's basically how we start and stop water hoses, right? Or garden hoses. So we're going to use the same principle here. The switch, if I tried to turn this current path off with a switch, I would have to get some real beefy, powerful switch. Would be very expensive. I mean, you can do it, but why? Why do that when the valves are so cheap and plentiful and easy to use? So we're going to put a valve in place here. And as it happens, we already have that valve. That valve is right here. This MOSFET that we're using for Q2, this is essentially a valve if you wire it up one way. Now, the way it's working out right here is that this is actually that feedback mechanism that helps control the current that's flowing through our LED, but it can also be used as a valve or as a switch. You can look it up online, use a MOSFET as a switch, and that's what we're going to do here. We're going to use this MOSFET as a switch in order to replicate or emulate these valves that we have. So I've created a bit of a schematic here just to show you. So this is the same schematic here, but I've augmented it a little. All right, so it's the same thing. We can still have our 3 current paths, as you saw earlier. We still have our 3 resistors, we still have our 3 switches, but there's a difference, of course, right? I've moved the switch up over here, and I've added those MOSFETs in the current path. So the switch isn't actually blocking the current. It's the MOSFET that's going to be blocking the current, and the switch is going to be turning it on or off. So the way this works is, remember, these MOSFETs are voltage controlled, and the voltage at the gate, which is that point right over there, if that voltage is low, or let's say grounded or 0, then this MOSFET is an open circuit and it will not allow any current to pass. The valve is open. If I put a 5 volt or a high voltage at this point, then that closes that valve. So now I've closed the valve, and that means that the current can flow through this path freely. So what I need to do is adjust the amount of voltage at this point, and that's what this switch is doing. The way this is wired up right now is that this switch, when open, this circuit over here is broken, and this resistor, this 10 kilo ohm resistor over here, there's no current flowing through here. So the voltage at that point is going to be 0, meaning this switch is open, that MOSFET or the valve is open. No current flows. If I push that switch down, then I have current flowing in the switch circuit, which is not a lot, by the way, because this 10 kilo ohm resistor is going to make sure that this circuit flowing through the switch is very low, like half a milliamp or something. So it's going to be quite low. But I will have 5 volts at this point if my supply is 5 volts. And so that means that this MOSFET or valve is going to turn on and allow current to flow. So this will suffice very nicely for our purposes and allow us to control the current going through each and every one of these valves. So I'm going to use the exact same MOSFET that I have already in my circuit. This, if you recall from prior, was a BS270 MOSFET. I'm just going to use the same one. Why? Because I got them. And the other reason, I also put a 10 kilo ohm resistor here. I'm using 10 kilo ohms for 2 reasons. One, because it keeps the current very low through the switch, which is what we want, half a milliamp. But also, I got them. I got 10 kilo ohm resistors here, so that's what we're going to use. All right, let me show you the platform that we're going to build on. So let me just bring this over here, and you can see it. Okay. Okay, I'm trying to get the whole thing on the screen, but it doesn't look like I'm going to be able to do that. So I'm going to hide the schematic now, and hopefully let's see if I can bring it back up in a little bit. But here are the parts that we're going to use. Okay, so these 3 pieces here, I'm going to get my tweezers. These 3 things here are the switches, and there it is. You can kind of see the switch as we kind of handle it. Just a regular switch. They're cheap and easy to get. Obviously, they don't handle a lot of current, but that's the point. We want to be able to use cheap switches to be able to run this. These are the 3 MOSFETs. These are the exact same MOSFETs that I have in my circuit already. Here are my 10 kilo ohm resistors, and here are my parachute resistors. I'm supposed to have 3. The other one's still in the circuit. So what I did is, this is the same circuit we built a few videos ago. I've just moved it over to the side of the breadboard to make room for the rest of our circuit. So it's the exact same circuit we had before. There's the original MOSFET. This MOSFET I'm pointing at right here is the same MOSFET that's here. These are the BS270. And then down here is the transistor. So this is the 2N3904 transistor. And these 2 together make that feedback circuit. And then we have that 1 kilo ohm resistor feeding in the gate of the MOSFET. And here is that 6.2 ohm parachute resistor that was part of our original circuit. And here's the LED. So just to make sure everyone still believes it works, I'm going to plug it in, power it up, and look at that. There's our LED. Nice and bright, and it's working as expected at 105 milliamps. So actually, here's what we can do. I can show you the meter that I also have hooked up, and the meter will show. There it is. That's 105 milliamps on the meter. All right. Perfect. So let's continue, and I'm going to put this together. Okay, so bear with me for a while while I assemble this. You can watch me assemble it. It's going to go pretty quick, but I'll show you when it's done, and we'll be able to review what's happened. Okay, here we go. All right, I think I've been able to get everything onto the screen as I possibly can. Okay, so let's follow along what's happening here. So remember, this contraption over here, the circuit is pretty much the exact same as it was before. And then I have these green leads, and these green wires are basically let's call it the distribution. So this is where the current path's going to come in, and it's going to split, and it's going to send it off onto the 3 different resistors. Those are the green lines that we have over there. And the switches, of course, these are all down here. These switches are wired up so that they're fed from the power rail. That's the yellow line going in. And each switch, also on the other side of the switch, has that 10K resistor going to ground. So yellow line coming in from the power through the switch, and the 10K resistor going to ground. And the other side of that base of the other side of the gate of that MOSFET is connected to the other end of that switch. So that's basically how this is connected. And of course we have our at the other end of that green line, we have our parachute resistors of 3 varying sizes. So I forget which order I did them in. I actually think I did this one as a 6.2 and this one as the, okay, so well, that's okay. I'll figure it out as we go, but we'll arrange that. But they're in order. So they're 6, 12, and 24, or 6, 12, and 24. I don't actually remember which order I did them in. But that's it. This is wired up the way that it should be running. So let's plug it in and see what happens. All right. So I'm going to get my power connection and turn this on. All right, here we go. Now, let's see which one is which. Oh yeah, definitely. Okay, that works. So the one on the left turned out to be the lowest resistor. So this one is the 24 ohm. This switch over here is the 12 ohm. And this switch over here is the 6 ohm. So you know what I'll do is I'll actually flip it around because it'll match with the schematic over here. Let me just bear with me while I flip these things around so it aligns with the way the schematic is supposed to be. Or it aligns with the way I actually drew the schematic. So let's do that. All right, perfect. So it's lined up properly. Now, so you can kind of tell when I did that, the intensity of the LED changed. So let's go with the small intensity first, and we can see the intensity there. And here's the second switch. So this is going to be the next intensity, and the final switch, which is the peak intensity. So 3 switches gives us different intensity. But remember, the combination of the switches will give us more intensity as well. So if you remember the way the old chart used to work, here, let me bring that chart back up so you can actually see this. We don't need the circuit anymore. In fact, what I'll do is I'll put the chart up here. That's going to be far more useful for us than this schematic. There it is. There's our chart. Okay, and how can I do this? I'll bring this down here. I'll do it this way, just so we can see the chart. Okay, so what this means is that this switch on the left is this line. This switch in the middle is this one right over here. And this switch, of course, is this. So this is going to give us presumably 25 milliamps. If I put this one, it's 50. And if I put them together, it should be a little bit brighter at 75. And then if I get this one, it'll be even brighter. So let me do them in order. In fact, what I'll do is I'm going to number these, actually. Let me number them. So I'm going to number this 1, 2, 3, 4, 5, 6, 7. Okay, and I'll just go through the intensities by pushing the right button. So here's 1, 2, 3, 4, 5, 6, 7. Yeah, that worked really well. It worked really well for me, but of course you may not have been able to see the LED. So let me do that again, but this time, here, watch the LED. I'll bring it close so you can actually see the LED. Oh gosh, gotta put this up on the camera, make sure everyone can see what it is that we're doing here. Okay, try it again. So I'll do the same thing. Okay, so this is 1, 2, 3, 4, 5, 6, 7. Not bad. Now, take a look at the scope that I have here on the side here. The scope should read, watch the same thing. I'll go through the same count, but watch the scope now, okay? So 1, 2, 3, 4, 5, 6, 7. Not bad. Not bad at all. Very, very good. Now, if you notice something, if you look at the calculations we had, at 7, we should be at 175 milliamps. But let me put this all back up here to 7 and take a look at the scope. We're not quite at 175. It looks to be a little bit less. It looks to be about 150, maybe 155 or so. We're not quite there yet. In fact, if I just do the first one, right? If I just do the first one here to get 100 milliamps, just one switch, look at where we're at. It's actually a little less than 100. Now remember, before we should be getting 105 because this isn't actually 6 ohms. This is 6.2 ohms. So we should be getting 105. This time we're actually getting less than 100. So what's going on here? There's something very interesting going on here. There's also something else interesting going on as well. If I don't push any of the switches, I got no current flow. But look at my LED. It's actually glowing very dim. So what else is happening? Because there's something else fishy going on here as well. So we're going to have to figure out why my LED is glowing dim even though I haven't pushed any of the buttons, and also why I can't seem to get the right current out of here. Well, which one do we want to tackle first? Let me, you know what? I'm going to tackle the problem about not getting the right current, because this one would require a little bit of explanation. So let me get into that right here, and I'm going to quickly bring up the screen here. So let me do that. I'm going to pull up the other screen. There we go. Okay, so this is going to help us understand what's actually happening here with this. Why we're not getting the right current. So if you look at, this is the BS270 transistor. Sorry. Yeah, well, it is a transistor. It's the MOSFET that we're using. But this BS270 MOSFET actually says that, if I scroll down a little bit here, keep scrolling, keep scrolling, keep scrolling. Ah, there it is. Is it it? Yeah, there it is. So look at this. This is the on characteristic. So this tells me what this MOSFET behaves like when it's on. And it first of all tells me a number of details here about the gate threshold voltage. Don't worry about that. The number I'm looking at is this one, RDS. So this says that a static drain source on resistance is going to be a value. And so it tells me the specifications for that value to occur at 10 volts and 500 milliamps, which we are not at, is about 1.2 ohms typically, and max at 2 ohms. We're probably closer to the second value here. 4.5 volts of the gate voltage and running, well, we're actually trying to run 100 milliamps through it, but this one says 75 milliamps. So we're closer to this. But look at this. This is telling us something. This is telling us that there is actually a resistance of the switch. So this valve that we've put up here, it's not actually a perfect valve, as you would expect. Let me bring that back over here. It's not a perfect valve. So let me go back to the other schematic momentarily. Get that out of the way. Here we go. So these MOSFETs here, we made the analogy of these being like a valve, and I turn it on, therefore the valve is closed and current will flow. Well, it does flow, but there is a resistance inherent in this valve, and that's what this data sheet is telling us. This data sheet is telling us right here that there is an on resistance of probably somewhere around the realm of 1.8 to 3 volts. This is significant because if you remember, our resistor 1 here is 6.2 ohms. And if suddenly we have a resistance across this MOSFET of, it could be as much as 3 ohms, well, now the resistance in this path is no longer 6.2 ohms. It's actually closer to 9 ohms. This is going to be a lot higher than we expect. And what happens when we increase resistance? We lower the current. So that's why we're not getting all the current we should be getting, because we actually have a higher resistance due to this MOSFET. So we need to figure out a way to deal with this. So we'll figure that out in a future video, is how we can actually deal with this MOSFET. And while we're at it, we're also going to figure out in a future video as to why I have this mysterious phantom glowing resistor, even though I haven't plugged anything in. We're going to figure that out in a future video as well. And while we're at it, another thing I'd like to figure out in a future video, well, you can see that this works in principle. Once I figure out the other two things, I'm going to be able to understand why or how to get these switches to work in order to adjust the intensity. But practically speaking, we're not going to ask our the users or the people using the system to try to get proper patterns in their switches in order to make the intensity change. That's not going to be realistic. We're going to want to control these switches digitally. So that's another thing that we're going to get to as well, is control these switches digitally. Now, I can't do all of that on the next video, so what do you think? Which one should we be tackling on the next video? You know what? I'm not going to decide right now. I'll decide between now and the time I make the next video. So until then, we're going to tackle some, well, not all of it. We're going to tackle some of these issues on the next video that we have with our circuit. But I hope you enjoyed the build. I certainly did. Until next time.